Okay, can I just start?
Yeah, please.
Okay, thank you very much for the introduction. I apologize. Unfortunately, I picked up a COVID last week and had to cancel my trip in the last moment, so which I regret very much. Anyway, let me give you, since I noticed that I'm a little bit off the topic of the session, let's see this talk as a kind of entertaining, giving you a status report where we are currently with respect to understanding how magnetic skyrmionic textures interact in proximity to a superconductor. Let me also mention that the work that I'm going to present has been done in collaboration with my PhD students, Amita here, and also with our senior colleague Anatoly Volkov, from whom we benefit a lot looking and learning about these heterostructures. Although, of course, I'm not only going to talk about our work, but also give you a little bit of an overview on the subject. Now, you know very well, you have had, I think, at least one plenary talk on the subject, why you would be initially interested in looking into the proximity effect between a superconductor and the ferromagnet. And one of the major application currently in this field is the superconducting spintronics, which is basically based on the fact that you can have a long-range proximity effect between two superconductors which is sandwiched with a ferromagnet. And the idea comes from the virtue that from the discoveries that has been done by Bergeret, Volkov, and Efetov, and also a number of other groups. There is a number of reviews on this, which I'm citing here. I'm also citing original papers on the next slide. But the idea is the following. So you have a superconductor, which is typically a spin singlet superconductor. So what is known is that if you have a ferromagnet and you have an inhomogeneous magnetization at the interface between the ferromagnet and the superconductor, what is actually happening is that the quantization axis is rotating. So which basically means that when spin singlet Cooper pair wave function, which penetrates into the ferromagnet, its quantization axis starts to rotate. And what actually is happening, so the first you do a spin mixing, and the second thing, because of the spin rotation out of the originally a spin triplet component, which is a total S equal to 0, you can create, by virtue of the quantization of the rotation of the quantization of the spin axis, you can create a component of the Cooper pair wave function, which is spin polarized. And the spin polarized component will be insensitive to the magnetization in your ferromagnet that can penetrate to a large distance. So this is something that has been theoretically predicted and also has been experimentally realized, and there is a number of groups which are working on this field. So this is, for example, one of the early experiments on this field, where you have two superconductor and you have a spiral ferromagnet with rotating magnetization and a ferromagnet by cobalt, where you can clearly see that without holmium, so without this rotation, without this spin spiral, your Josephson current is strongly suppressed. And if you have the spiral ferromagnet, then what is happening is that you have a long-range proximity effect, and your current voltage, so your Josephson current exists up to a much longer cobalt thickness, which of course also interesting because you can also try to polarize this current, and this is the reason why it's interesting for the superconducting spintronic. This is a field on its own, but now I'm going to ask a question: what happens if you take such a heterostructures and you consider a chiral magnet which hosts magnetic skyrmions? From the very beginning, again, it seems naturally that such a heterostructures with also rotating magnetization might be interesting from the perspective of the spintronics, but also there is another reason why recently people have been looking on this, I'm going to tell you in a little moment about this. So let me just, for those of you who are not working in the field of skyrmions, let me just remind you that this is a topological texture that can be characterized by a particular homotopy group, which is which is basically mapping physical space spin orientation to the order parameter space. And in this case, for the skyrmions, you have spins with a fixed length on the two-dimensional plane, and your order parameter is a 3D magnetization. So what is actually happening is that your order parameter space becomes a surface of a sphere described by the two angles as 2. And you can have topological defects which you cannot easily remove in this case. And the most simplest examples of this are this simplest n equal to 1 topological texture, which are either Niel or block skyrmions. And this is the example of the mapping to the order parameter space. And you can compute this winding number by simply looking on the changes of the magnetization. Again, originally this has been of interest in the field of high energy or particle physics, because Tony Skyrmion proposed this object as a possible explanation for the formation of the elementary particles. But it actually very quickly also became interesting for the condensed matter system. So the first who've been looking on it were Belavin and Polyakov, who looked into the context of the nonlinear sigma model before Bogdanov and Jablonski in a ferromagnet, but actually the realization or the proposal to realize this magnetic skyrmions in the form of the skyrmionic lattices came by Bogdanov and Jablonski back in 1989, where they were playing around with energy magnetization, total magnetization energy of a ferromagnet, which can, with a strong Dzerzhinsky-Maury interaction, so which means with a strong spin-orbit coupling. And they have found that if you put the system in the external magnetic field, of course, you can also have other terms like crystalline anisotropy and so on. If you change the field, applied field, you start from a helical phase and you reach upon saturation fields, the ferromagnetic arrangement. But there is also another phase in between, which is a skyrmionic crystal, which is thermodynamically stable, in contrast to the single skyrmions, which are usually metastable objects. And they have been successfully realized by Mühlbauer et al. In 2008. Actually, for the sake of the story, one has to remind that this A phase has been indeed seen in MNSI. This is a system which indeed can be, let's say, to a first approximation described by this Hamiltonian. The presence of the A phase was known for some time, but actually Mühlbauer was the first one who successfully shown that this phase is indeed corresponds to the skyrmionic crystal. And now, again, just for the sake of the further presentation, so these are our object, chiral skyrmions, Niel and block skyrmions. And now let me also mention that these are the objects which are also familiar in the field of superconducting spintronics, because you can look on it as if you make a cut along one of the radial direction, you will see that although the topology is lost, but you still have a very similar texture that as domain walls, Niel and the block type of the domain walls. Okay, so now what is interesting is that this field is really booming in the book. So there is a number of, every year there are new materials which are discovered to find to host skyrmions of the different types, and this is one of the most recent review by Takura and Kanazawa, where they see this objects. And what is also interesting that the temperature range where they see it is also very different. And what is interesting from the perspective of the superconductor is that they also see this skyrmions either as a metastable objects or like skyrmionic crystal, also at the very, very low temperatures. And which makes them an interesting object also to study in proximity to a superconductor. Now, let me come apart from the superconducting spintronics. The reason why people started to look into this heterostructure is actually driven by the obsession of the field to find the Majorana bound states. Let me just remind you the original proposal that you have an S5 superconductor, you have a semiconductor, you have a wire with a strong spin-orbit coupling like an indium antimonium, and you apply a field along the x direction. And in that case, what is has been shown by virtue of the very simple calculation that indeed what is happening if you start with a simple two-dimensional electron gas, you split it by the virtue of the spin-orbit coupling, you apply the Zeeman field, and if you tune the parameter in the right regime, the Fermi level is crossing only one of the bands, and this band will be hosting spinless fermions. If now you put a S-wave superconductor in proximity to it, you will actually realize a topological superconductivity which should host Majorana skyrmions. And now let me tell you that here you have basically a magnetic exchange field, a spin-orbit coupling. And in principle, magnetic structure as a skyrmion has both. It has an exchange field, and it's much larger than just an external magnetic field, and you have also an intrinsic spin-orbit coupling, like a Zemlinsky-Maury interaction, which basically tells you that such a skyrmionic texture can be an interesting platform to realize topological superconductivity. And this was the reason why people also started to look into this, and you can nicely show that if you have this rotating magnetization, if you have a basically, which you can describe by the local unitary transformation, you can basically show that by taking, if you assume that you have such a heterostructure, we have now a superconductor and a ferromagnet, and you have some two-dimensional electron guns which forms at the interface between those two, you can show that in this case, by the virtual proximity, you have superconductivity, and on this superconductor, you have an action of the effective spin-orbit coupling, which you can derive from the magnetization. And you can see that by doing this simple transformation, you can see that indeed having an Zemlinsky-Maury interaction can be then mapped back, so to speak, into the effective Rashba type of spin-orbit coupling. And then if you tune again some parameters, the hope was that you can again realize Majorana bound state and topological superconductivity in the proximity between both. Okay, so what is about the experimental and theoretical situation? So the theoretical problem that has been realized is that it actually turns out that for the simplest skyrmion that you see, namely Niel and block type of the skyrmions for the ±1 vorticity, it turns out that the Majorana bound states do not form. So you need to do something more. For example, if you go to the higher vorticity, so if you go to the even vorticity, you can indeed show that in such a case, you indeed can realize a Majorana bound state, but one of the immediate problems is that it's very hard to realize experimentally such a skyrmionic structure. Then there has been proposals that you can play with elongated skyrmions, although it's also controversial whether you can or you cannot see a Majorana bound state in this case. And finally, there has been recent proposals that if you look at the skyrmionic lattices, then if you, so such a skyrmionic lattice will be a whole platform for looking for such a Majorana bound state, and depending again on the number of parameters and depending on the position where you're located, you will be able to see, you should be able to see the Majorana fermions. But as you see already on the theory side, the situation regarding the finding Majorana appears to be quite complex. Regarding the experimental situation, it's also a little bit of a problem because you need to basically bring material which hosts skyrmions. This is, for example, one of the realizations that has been done by the Wiesendanger and collaborators, Kirsten von Bergmann, where they brought palladium iron iridate and were successfully showing that you do have formation of the skyrmions, which you can see, for example, here on the top of the rhenium 0001 surface. However, one of the problem always is that they had in this experiment is to prove unambiguously that there is an interaction of superconductivity with skyrmion. But this is one of the first attempts. Then there was another experimental realization where people wrote a cobalt monolayer also on the ruthenium. Here it's on the rhenium, here it's on the ruthenium layer. That's all type 1 superconductors. And actually it turns out that indeed, again, they were able to show that in such a heterostructure, they do see a formation of the skyrmionic objects. But again, what was essentially still missing is to show that there is an interaction between a superconducting substrate with corresponding skyrmion. So, and then there was another proposal from France where they looked into the molybdenum silicate on platinum, cobalt, ruthenium, where they saw some signatures also of the interaction between skyrmions, or probably some effect of the stray fields, which they saw in the flux spinning in a superconductors, where they could clearly see that there is some interaction between the two, basically two parts of the interfaces. However, still the problem was that they could not unambiguously show that they could see skyrmionic stabilities. So this brings me to another question. So if it turns out that looking into the skyrmionic superconducting heterostructures is maybe not beneficial at the first glance to realize Majorana skyrmions, Majorana fermions, you can ask another question. And the question that we were also looking at is, in principle, you can also ask whether this type of topological defects can interact. So we know that in a superconductor you have a precursor vortices, in a chiral magnet you have block or near skyrmions. These are topological defects, and the natural question arises: how do they interact with each other? And the original proposal was made by Mark Radner and Christian Heiss and collaborators, where they actually proposed that such an interaction may occur if there is a so-called superconducting magneto-electric effect. So which basically requires that if you have your skyrmions, it basically is a polarization of the skyrmion generates some supercurrents, and such are supercurrents by the virtue of the spin orbit coupling start to interact with superconducting vortex. They basically propose that if the spin orbit coupling is relatively large, then the supercurrent indeed, which is basically created by the skyrmionic stray fields, should generate vortices. Now, we looked on this problem on a simpler basis by essentially suggesting, well, maybe we can consider on the problem on the different side. So let's assume that there is no proximity in a certain sense. Let's assume that there is no direct interaction between your chiral magnet and the superconductor. So we even assume that you can put an insulator which prevents to have direct exchange interaction. And this is something that typically you don't even need to create. It's something which is created automatically when you create such a structure. And the only way they interact is that, of course, we know that in a type 2 superconductors, you apply an external field, you will generate vortices, and these vortices will have also large stray fields, and this stray field of the vortex can actually interact with a skyrmion. So there is no direct proximity effect. The only interaction is virtue of the electromagnetic field, but the electromagnetic coupling. Okay, so then you take basically, in order to strengthen the effect, you take a thin film, and we know that in the thin film, when the penetration length is much larger than the thickness of a superconductor, you have pure vortices. And good advantage of these pure vortices is that they are weakly screened, so their stray field is going well beyond the superconducting film. And it has also a characteristic length, lambda, which is lambda squared over dsc, which is giving you the size of the pore length, which can change up to 1 millimeter. And this is something that you can also change experimentally. And also you have a long range vortex field. Okay, so then the idea that you are going to do is exactly the same that Bogdanov and Yablonsky has considered, except that now you add an extra term. So imagine you have a chiral magnet, which do not have a direct interaction with a superconductor. And the only interaction you have, because you have, by the application of the external field, you also create vortices. And this vortices has a profile. And of course, the profile of this vortex field will start to interact with a profile of your skyrmion magnetization. So essentially, by assuming, or by basically solving, assuming that you're in the regime where there are individual skyrmions or skyrmion lattices, and you have a vortex lattice, you start to interact by the virtue of this interaction. Okay, and then if you do so, then this is how the interaction energy can be described in this case. So this is your usual terms. You have a chiral magnet plus the stray field from the ferrovortex. And of course, it's not a surprise that depending on the polarity of the vortex, you do generate attractive interaction, depending on whether, and you see that this is the case actually, independent whether the typical size of the vortex is much bigger than the skyrmion radius or other way around. In both cases, you can generate attractive forces for a certain polarity and repulsive forces. Now, in order to see whether the whole configuration is thermodynamically stable, so you now try to minimize total energy, assuming that you have a skyrmionic and vortice lattices, and you look the condition for the total minimum of the energy, and there you can actually see is that if you do so, that the configuration is actually stable, despite the fact that initially we saw that the attractive forces are generated for both cases. But if you start to look into the thermodynamic stability, you see that it's actually only stable if you are dealing with a large skyrmion radius. So the skyrmion is larger than the typical length of the vortex. This is all very nice. So that's basically if you now summarize what you want to have. So for the exchange coupling, so that's the one which was proposed by Radner and collaborators, that they argued that you can have skyrmion-induced current must spatially coincide with the vortex current to reduce the total free energy of the superconductor, and they put a condition when it can happen. Whereas for the stray field, we also formulated the condition under which the skyrmion's vortex pairs will be stable. Okay, so now let me mention that such a proposal that has been made has been recently realized. Let me just spend 1 or 2 slides on this. So again, the problem is in this community is that you need to have 2 types of, so you need to have experimental groups which are experts in both, basically in the skyrmions, because you need to find an optimal balance to modulate the skyrmion radius and the skyrmion stray field amplitude. And at the same time, it has to be someone who is also is familiar with the field of superconductors, because you need to also optimize your superconducting field. And so this both combined in the group of Christoph Panagopoulos in Singapore, where they made some engineering in order to find an ideal match of, let's say, elements containing so iron, cobalt, platinum, and iridium in order to model the strengths of the Jelesinski-Maury interaction to optimize the size of the skyrmions. And this is what they did here. For these heterostructures of the 47 nanometers, and at the same time, they also found the superconductor niobium platinum, and which they also put with a certain. So this is niobium 25, and they put some coverage with platinum in order to effectively fix or modify coherence, superconducting coherence length, and that's of course done in order to modify the size of the vortices. And this is also what they have shown here that they were able to do. And now they match both. And actually they were looking, and the paper has been published last year. What is interesting is that they try to see essentially 2 effects. So they try to see the effect that we have predicted, where you have an insulator, where you try to avoid the Edelstein effect, and the only way the 2 heterostructures are interacting with each other are only by the virtue of the stray fields. Or you can also have a direct contact. Of course, stray fields will be interacting also, but in addition, you also expect to see maybe effects related to the stray fields, to the Edelstein effect. And if you now compare the numbers that you get, that they measured in all of this substrate, you see that you have exactly the conditions that we have been proposing, whereas skyrmionic radius is larger than the corresponding coherence lengths, the corresponding size of the vortex, and all of them are much smaller than the lambda. Okay. So first, they indeed have been able to successfully show that indeed there is an interaction. This is measurement of the bulk magnetization, and you clearly see that in contrast to the typical behavior of a superconductor, you see indeed a transition that is basically connected to the formation of the to the skyrmion nucleation field that they see here, and they see that the effect is changing in this going from the heterostructure with the insulator in between to the and the superconductor, so which basically clearly argues that they indeed see the formation of both vortices and skyrmions, and they see a strong anti-vortex response in MS fields because they see a larger drop in this case, and this is all a very good indicative factor that they do see that they're both skyrmions and the vortices, and they do interact with each other. Then they also see that the skyrmion induced, so the skyrmion should also, the stray field of the skyrmion should induce the critical current. This is also that have been discussed by us. And they also clearly see this in the range where the skyrmions appear. So they basically do see that the topological structure pin fluxons, and this is the first step why where they see that two types of textures start to interact with each other. Of course, that's still a thermodynamic probes, and they haven't managed yet to show spectroscopically or by help of, for example, raw and stems that they see both skyrmions and underneath of vortices, but this is something that I believe can be done. Now, let me come back to another proposal, to the proposal that I was saying is unsuccessful, namely the prediction that you can have maybe Majorana fermions underneath of a skyrmion in a superconductor. And I told you that the problem was that it appeared that for, excuse me, for the odd number of, for the odd vorticity of the skyrmion, this is not possible. It actually turns out, and this has been a proposal by the Karlsruhe group, that now if you have combined composite objects where you can combine a vorticity of the skyrmion and the vortex, it actually allows you to generate Majorana state, which is emerging at the skyrmion core. So which is again coming back to the question that such a composite texture, skyrmion vortex, might be now again interesting to look from the perspective of realizing Majorana fermions. Now, there has been another interesting proposal, basically about why to have such a pair would be advantageous. And the reason is that if you have, so one of the problem, for example, to have skyrmions, magnetic skyrmions for the application in various memory devices is that, surprisingly, is that skyrmion is a topological object. And the reason is that if you apply a current along x direction, there is a transverse movement, which is exactly connected to the skyrmion Hall effect. Therefore, skyrmion is really relatively difficult to manipulate in contrast to the domain wall, for example. Now, if you have a composite pair, that becomes also another interesting way of manipulating such a pair, because you can, of course, move the vortices and the skyrmion. There has been a proposal by Milosevic and others. And of course, another proposal has been just published is that once you have this, so there has been a proposal, how can you scale such an object having Majorana fermions? Again, here theory is well ahead of the experimental realization, right? Okay, now nevertheless, let me now spend the last 2 minutes on the other interesting points from where I began my talk. Remember, I mentioned that the initial interest in looking on the inhomogeneous magnetization in a superconductor in a magnet is that you can arrange to have a long-range proximity. So now coming back to the true proximity effect, so one of the interesting proposal would be that once you have a skyrmion, which is at the interface with a superconductor, of course, it will also create, you can understand in the following ways, that it will create the Cooper pairs, And the Cooper pairs on the superconducting side will try to reflect, of course, the profile of the skyrmion, which will be on the ferromagnetic side. And that is interesting because it's in principle gives you a very sensitive way of looking on this interesting magnetic texture with a Fraunhofer pattern. And there should be a distinct pattern for magnetic skyrmion. That's one proposal. The other proposal is that, of course, if you have such a, skyrmions, and here it is such that I already mentioned that in many respects, the behavior of the skyrmions is very similar to the domain wall. So you can, for example, view a skyrmion as something which is two domain walls, which is elongated along this direction. You can see how the long-range triplet component is modified, and this is something that we have looked that the paper has been published this year. Depending on the various type of the filtering, you can get additional contribution, which you can either enhance various components or suppress, depending on whether you are looking on the charge current or on the spin current. Okay, I think my time is up, and let me now summarize. So I tried to give you a kind of an overview where we are in looking at interfaces hosting skyrmions and a superconductor. So first of all, there is a very interesting experimental realization of the composite pairs, the vortex-SKYRMIONs, which is interesting from the perspective of finding topological superconductivity and Majorana bound states. There is still something which is not fully explored, namely how the Josephson current is modified in presence of the skyrmions. But what we saw is that this Josephson current, if you are looking onto the skyrmions between two superconductors, you see that you can use the Josephson current because you can force torque on the skyrmion, forcing it to move, which is another way of manipulating skyrmion. And of course, another proposal is the inverse proximity effect, where the skyrmion should have given a special pattern for the Fraunhofer pattern. Okay, let me stop at this point, and thank you very much for your attention. Okay, Dima, I don't hear you if you're saying something. No, still don't hear you.
Okay.
Oh, now I hear you. Okay, great. Now again, not.
Okay. Do you hear?
Yes, now I hear. Yes.
Okay. Great questions. Okay. Let me then ask a question. So basically, now what you are told is this is basically technology of the some films on top of other films, skyrmions. What is the perspective for having monolayers superconducting and monolayers magnetic?
You mean now the question is whether you can have bulk material where you have both vortices and the skyrmions, or skyrmionic
okay.
type of
This
texture?
is the first question.
Or you
both.
Oh, you mean to have a material where you can do MBE in order to have a layer which is skyrmion and another one which is superconducting one? Well, this is a field of 2D materials. I know that there are realization. Actually, I think they are from TU Dresden, if I remember correctly, by one of your colleagues, experimental colleagues, which have shown that you can have realization of the skyrmions in some of the 2D magnets. I don't remember exactly the chemical composition. There is always a problem, as you know, that putting the system in contact with each other is that superconductivity is easily suppressed. is easily suppressed by putting, approximatized to a magnet, and that's one of the reasons why you would like actually to avoid the strong proximity. So far, I'm not aware of the realization in the field of 2D materials. Concerning about materials, there has been proposal, as you know, in some of the iron-based superconductors, there is a claim that you can have a magnetic phase, which is spin vortex, and such a spin vortex phase coexist with superconductivity. But there has been, I think, a work also from Copenhagen, from Brian Anderson group, where they try to see whether you can have some topological superconductivity occurring in this case. But again, it's pure theory consideration until now. Experimentally, I'm not aware.
Okay, one more question, if any. Okay, we are behind the schedule. Let us thank the speaker again. And the next talk is,
Thanks very much.